having learned a bit about radar imaging and its peculiarities, let's say, let's learn a little bit about Venus and its peculiarities. The two multiply together, unfortunately. So if we go back in time, the sort of first global information that we got from Venus was topography way back in the, well, around the end of the 70s, really, from the Pioneer Venus orbiter. There were some probes, they didn't image on the ground, but we got this sort of view of the planet where we could see continental areas and lowlands, and it was in some ways similar to the Earth, but already obviously very different. It's much flatter than the Earth is overall. And so we got the first sort of hints of something interesting going on. We actually also got our first radar images, but these were real aperture images. So essentially using the not doing synthetic aperture, but using the actual antenna. So they're very low resolution, about 100 kilometers resolution or so. But that is an image of the surface of Venus. We did also have images from the Earth from Arecibo, but they covered a much smaller area that we can see close up. I mean, oddly enough, and this is something we need to bear in mind when we're looking at radar images, we also had the first images of another planet are from Venus. The top left and top right images are were taken in the mid-1970s. So actually before Viking landed on Mars. And the top left Venera 9 image is probably the most interesting image from another planet, frankly, of the surface, because it shows a steep slope. It's probably around about 20 or 30 degrees. It's covered in scree. You can see all those boulders broken up. So that's an active slope. It's got coarse and fine material on it. And in this reprocessed image by Don Mitchell, where he's gone back to the original data, you can actually see the other side of the valley on the top left. And that's because the camera system starts at the horizon, scans down towards the ground and back up to the horizon on the other side in order to get a sort of, in the limited time they had, to get both near and far views of the surface. It gives this funny shaped image. But that is a tectonic valley, which we just don't see on most other surfaces. And indeed, even on Venera 13 in the distance there, you can see topography, you can see rough surfaces. So this is a planet already from those surface images, which is obviously remaking itself. And although all of these images are regarded as representing basaltic surfaces, they don't look like basaltic surfaces. They look like shales. They look like sandstones and things like that. They look sedimentary. They basaltic in composition, but they've been reworked in some way. And I find the Venera 10 image perhaps one of the most interesting because it's covered in this darker material, which I think you can see in the Venera 13. But that seems to be derived from high ground nearby, or in the distance, I should say, in the image, but it's not that far away, that judging from where it landed might well be tesserae. So this dark material might be derived from those tesserae. The next set of data that we got was from the Venera 1516 mission, which only imaged the North Pole of Venus down to about 25 degrees, 30 degrees latitude, and gave us topography on the right and some high resolution images on the left at about 1 kilometer resolution. But these images are strange because they were taken at very low incidence angle, 10 degrees or so, so almost from vertical. And then they were filtered to remove long wavelength artifacts, really, changes in brightness. So what you have is really a strongly shaded relief image. And this is Maxwell Montes, that's Cleopatra there. That's actually a very steep slope that Cleopatra is sitting on, but it's not obvious at all in the image. It's rough, but it's not obvious that that's a steep, high slope. Just while we're on the subject, that Vega also took some data from the surface. It didn't take images because it landed at night, but it did put 2 balloons, the only balloons so far to have gone to another planet, into the cloud deck and gave us a load of information over sort of 5 or 6 days there. But Magellan is the mission that really gave us the global view and the detail that we're still working on today from Venus. And that's because it used a SAR imaging system. And you can see that as the main antenna there in that image on the right. The little horn antenna to the left is the altimeter. The main dish is actually a spare from the Voyager missions. And it imaged using that SAR system over 3 sets of orbits, 3 cycles, we call them, or days of Venus, where Venus rotates very, very slowly. And the spacecraft essentially sits in one place and the planet turns underneath it, and you get eventually an image of the whole planet. It did that 3 times, and then it collected, did some aerobraking and other features, and it collected gravity data and radio experiments for the rest of the time. And so this is a image coming from the JPL guide, which is really still the most useful guide you can get to Magellan image interpretation, and you can download it from that website now as a PDF. It used to be as a HTML pages, but they've changed it. And it explains exactly what they did. It's similar to the diagram I showed you earlier, except that it also had an altimeter, so that pointed to Nadir. Following on from Magellan, data that we shall also look at with the mapping later on, comes from Venus Express. And this is the mission that really changed our understanding of Venus, because it took images in the infrared. It wasn't designed to see the surface, but it happened that at the sort of 1 micron wave band where it was sensitive, you could see the ground because the ground is hot. And so you can see a number of features there around the south pole of Venus there. And including where it says alpha, a sort of low emissivity region. This is in infrared, of course, which corresponds to the low emissivity region in the radar, which is the tesserae at alpha radio. There's noise at the edges, so you can sort of ignore some of the red bits, but it's also told us where Imdir is, which is around the 210 degree line towards the southwest, sorry. You'll see a little red spot. We're going to be looking at that area in detail in the mapping area, exercise. And that red spot indicated recent activity. We don't know exactly what recent means. It might mean a few thousand years. It might mean a couple of million years, but it seems to be an active volcano. Now, of course, we have other evidence from ATLA of volcanic activity during the Magellan mission. And the mission that's currently there now, Akatsuki, is a real survivor, but it gave us also another big surprise, which was the relationship between the surface and the atmosphere. It was exclusively an atmospheric mission, but it detected the waves, which you can see on the right, in the upper atmosphere, in the clouds, generated by winds blowing over the surface, blowing over Aphrodite Terra. And that is really unexpected. And it's given us the possibility of detecting waves from earthquakes on Venus, or Venus quakes. But it's also shown us that actually there's a much closer relationship between the surface and the atmosphere than we ever realized. And we need to understand that when we're looking at surface processes. But the thing I want to draw you to is something that is really special about Venus and makes it most interesting to me as an Earth scientist. And that is its size. Earth and Venus are enormous compared to other terrestrial planets. They are more or less 10 times the mass of Mars, which is the next largest rocky planet. And you can see that as you go from Mars down to the moon, you're looking at basically one plate planets that what may be initially hot, generate some volcanism, flood the interiors of craters, but don't really recreate their surface in any real way, and they just slowly cool down. Mars got closest to it, to mobility. It generated some rift systems and some big volcanoes, but the size of those volcanoes tells you that Mars never really became a mobile surface. Whereas Venus and Earth are both totally reformed and reshaped by tectonism and volcanism. and they are the dominant processes on both planets, modified by sedimentary processes, of course, in both cases, actually. But what's generating those surfaces is tectonics and volcanics, and that is driven by internal heat. So they are fundamentally different planets, and the techniques that we use to map the Moon, Mercury, and Mars do not apply to Venus, and we have to use techniques that we use on the Earth when we're looking at Venus. But that isn't what happened. In the first instance, straight after Magellan, people did a lot of mapping in a traditional way, looking for features, classifying them, making inventories. Here we have a map of the volcanic features on Venus. You see there's a huge concentration in the right-hand side here in an area called the Beta Atlathymus or Bat region of Venus, where half the Venus volcanoes actually reside, or at least half the large ones. There are 85,000 small volcanoes that have been mapped recently, that are a bit more concentrated in the plains. You'll also notice that there are places where there are very few volcanoes and there's high ground, and these high standing tertiary areas I'll mention a bit later on. So let's go through some of these features and see what they look like, because that in itself I think will be quite informative about what we're seeing here. This is a large volcano. It's now called Deseto Corona. It's because the caldera is a sort of oval shape in the top left of the right-hand image. But actually it's a large volcano. It's probably a collapsed magma chamber where the caldera is. And all of that area in the center of the image are lava flows. And they go over that mountain range running down the middle of the image and flood the plains on the right-hand side. And you can see a number of things about that in the radar image. So you can see it's very bright and rough on the right-hand side because it flowed very fast as it flooded out into those plains. And the tips of the flows are also rough and bright because that's where the flow is being reworked all the time. But the main body of the flows, you can see subtle boundaries between them, but they're basically much smoother surfaces because they have a sort of constant crust. But the thing of real interest are the lava channels coming down the southern side and sweeping round towards the mountains. And there's a zoom in there of those lava channels. And you can see teardrop-shaped islands, you can see meanders, cross-cutting channels. It's a sort of braided system, but it is lava. And this is really a volcano that we don't see on the Earth today, but we do see in the past. I think of this as Mull or Skye in Scotland. During the Atlantic breakup, but during any kind of big plume event, big breakup, continental breakup, we see these really big volcanoes, and we call these flood basalts. But actually, you can see that they're big channels and they're really big flows. They're just scaled up versions of the smaller features that we see. There are caldera on Venus, and most of them, if not all of them, really, that we can see are probably basaltic, so they're collapsed magma chambers at the top, just like we see on Mars, for instance, here, Sacagawea here, showing exactly that. There are some unusual volcanoes on Venus. On the lower left, there are things called Faro, which are known as pancake domes, and because they look like Scotch pancakes, really. And there's a big debate about what their composition is, because they are clearly viscous. They could be therefore more rhyolitic in composition, but actually I think they can be generated by sort of basalts or similar sorts of materials. And then there are sinuous river-like channels or canali on Venus. And this one here, I generated some very high resolution topography from stereo, and you can see it flowing through a thrust belt system, and it's bending around it, which is showing that it was active at the same time as those thrusts were developing. But they look like river channels, and they flow quite large distances. There are different types, really. These ones are definitely volcanic, because I know where they come from the volcano they come from. But there are others that would appear to be like submarine channels on the Earth, that might be density currents or other features like that. And then there's these unique features to Venus called corona, which are loosely circular features. They have an annulus, a ring around some sort of volcanic center. That center may be growing, developing, fracturing, like you see on the bottom right, or it may be flooded and resurfaced by volcanism, you see on the left there. But they have this characteristic annulus, which is usually a trough and a ridge, just like a motte and bailey, I suppose, of a castle system. And they are thought to be the expression of the surface expression of intrusions, diapirs, batholiths, that sort of thing, on coming up into the crust or in through the lithosphere and the crust. And there are hundreds of them on Venus. So it hints that there are thousands of volcanoes, there are hundreds of coronae, there's a lot of magmatic activity on Venus that we need to be aware of. The other feature that is unique to Venus, although we see something similar on the Earth, are called tessera. And these are really quite highly deformed terrains. And it can be difficult to work out the structural history of these areas. And this is Alpha Regio, which is where Da Vinci will land, somewhere in this, to the left and middle of, I think, of this area. And you can see it's a really quite complex looking terrain. There are some volcanic features. There do appear to be some, valleys flooded with lavas and little volcanoes. In fact, the pancake domes are off at the bottom right there. But by and large, these are tectonically deformed. And they are often high standing, and they look a little bit like our continental regions on the Earth. So in the sort of end of all this process, we generate maps of the surface of Venus of different features on the surface and try to understand them. But the one problem that we really have with this is that we don't know how old the surface is. All we have are the impact craters. And unlike the Moon, Mercury, or Mars, they are problematic when it comes to dating the surface, as I'll explain in a moment. And so we look at this surface and we don't know where the activity is. If we had the information we have on the Earth, we might see on the Earth thousands of volcanoes, but only a couple of thousand that are actually active, and they are running along in certain areas like plate boundaries. Because we can't see that on Venus, we just see this scattering of processes which might have taken 500 million years to develop. And so it's harder to make sense of what's going on now and what's driving the planet. And that's because there are only about 950 impact craters on the surface of Venus, and they are scattered across the surface pretty much at random, at least spatially. They're not at random with respect to a few other things, but they are pretty much random across the surface. And what that means is that we cannot resolve areas of any significant size that are older or younger than other areas. So one thing we can say, there's no Pacific Ocean on Venus. There's nothing on the scale of a quarter of the planet that is significantly younger than another area of the planet. But what we can't say is that there's no area the age of the Pacific Ocean. There's no area the age of our cratons. In fact, there probably are both, but they are small and scattered across the surface. So we can't distinguish them. So that's the kind of conventional view of the surface, and there are detailed global maps that you can look up. This is just one example. It's probably the most detailed example there is, showing you all the different features on the surface, and in particular distinguishing different planes units, different features across the surface, and correlating them. Because we can't date the surface, we can do stratigraphy. We can look at the relative ages of things by looking at their cross-cutting relationships. But this is where we fall foul of radar. So just to go into some detail, I'm not picking on these two in particular, it's just they have really good examples of what is a common practice. Here on the top left is an area of tessera, and you can see there's a ridge and some slopes and a flat, what looks like a flat valley floor. And I want you to bear in mind the impact crater we saw in the previous hour, of that ejecta blanket, what it looks like. The way this is interpreted by looking at it as an image, as a photograph really, is to say that those three brightness levels. Let's see if I, oh gosh, my screen's just died. I hope it didn't die for you. Right, let me get the laser pointer up. So this bright area, let's map that as one unit. These areas here, let's map that as another unit. And then this low-lying area here, let's map as a third unit. These are different kinds of planes. Well, that's not the case at all. This is a radar image of Death Valley in Nevada. And you can see the rough, bright tops of mountains here. And coming off them are scree slopes, which we call alluvial fans, and they gradually get finer and finer and finer down into the valley bottoms. If you were to walk down that slope, you would see no boundary. But because, if you remember the ejector, the radar is so sensitive to grain size, at the spatial resolution of the radar, there seems to be a very sharp change in brightness because we are going from something that is roughly gravelly to something that is roughly sandy, and from rocks down to gravel and so on. And so we see boundaries that aren't really there. And that is the fundamental problem that we have with these radar images. And if we apply the left and right techniques and look at those surfaces, we can see actually quite a lot of other subtle features. But we can see that these are indeed scree slopes coming down into that valley floor there from these high ridges up here, which is exposed bedrock. And so this is just an active slope process, filling the valley floor with fine-grained material. And in fact, under the Venus atmosphere, sand will saltate and move, forming dunes. And it looks like there are indeed sort of ripples running down this valley, generated by winds moving across the floor of the valley there. So that's one thing to bear in mind. And to give you another example of what we're not seeing, this is an example from Iceland, central Iceland, and we can see a volcano to the bottom left. That's Askja, and we can see a variety of different terrains. And if we just look at them with the mindset of classifying and thinking about what features they are, we will see mountains, we will see smooth plains, we will see ridged plains, and we will try and date them as being different ages and different surfaces. If we put on the actual geology, which we know in Iceland, we find that what we perhaps thought was one of the oldest features running through here, these old ridged plains, is actually the youngest, because that's the Mid-Atlantic Ridge. And these are, they have a covering of young pyroclastic fallout across this area, but actually these plains are quite old relative to the stream and everything that's running through the middle. And the youngest feature of all is this lava flow here, which doesn't even really show up, which was erupted in about 2014 or so. And that's interesting because if we look at this area in simulations of cycle 1 and cycle 2 with the same time separation, we can see quite a big change in the area and hence the volume of that lava flow between the two images. But because the geometry looks so different, because the image looks so different, it's not obvious at all that anything is different in that lava flow. So we might well have missed changes that have happened on the surface between cycles. And in fact, this is what Robbie Herrick picked up at Atla by comparing two sets of images of a crater, a volcanic crater, if you like, and seeing it change between those cycles. So what do we do? How do we map the surface of Venus? What do we look at? Well, we have to take a totally different approach to Venus. We have to take the approach we use on the Earth. And that is to look at the geomorphology, look at the landforms, and look at the relationships between them and interpret them. Now, that seems, in a sense, counterintuitive, in which surely we should do the interpretation last. But actually, that's what we do all the time. We always interpret. That's where those inventories come from. Here's a round feature. I'll map it as a round feature. Here's a volcano. I'll call it a volcano. We have to be careful about how we do this. And we have to think all the time that we're looking at radar data. But the key thing here is to look at the relationships that we can see. And in this example here, we're looking at a series of ridge belts, what's called ridge belts or rupas. This is really a mountain system. These are folds and thrusts. Now they look like they're verging to the left. And that is because the radar antenna is viewing this from the left. If we were to look from the other side, we would see them verge the other way. And we have to be careful of that. And that's also partly why I use the left and right images when they're available, to make sure that I'm really properly understanding the shape and the geometry. When they are more kind of oblique to the beam, they look a more realistic shape, and they look like rounded folds, periclines, that sort of thing. But we need to think about that. What is this? How is it generated? What's its relationships to the planes below or around them? We can see some lava flows. We can map some of these features out. So if you can see boundaries, we can make sense of them and we can map them out. But what we have to be conscious of and clear about is that just because this area has a sort of diffuse boundary here is just going from smoother to rougher and looks about the same as over here, it is not necessarily the same unit at all. So they may have exactly the same surface roughness, look the same to the radar, but be a completely different material unit. They may even have a geological boundary running underneath them that we cannot see because we're seeing the surface materials. So that is something to be very conscious of. Here's another example looking at a negative topography system, where we are seeing a trough and some fractures on either side. We're looking at essentially a rift system, but you can see there's much more complexity here. There's fractures cross-cutting, and there's association with lots of small volcanoes running through here. So again, we have to kind of think, what is going on? What is the relationships? What are these relationships telling us? And looking much more carefully about whether what the age relationships really are between these things. Are these volcanoes old and here all the time, and you can see some of the fractures cut right across them? Maybe that's right. Or are they actually magma coming up those fractures, erupting onto them, but then continuing to be fractured? Only really detailed mapping will reveal that. We have to be really careful. But when we do that, we start to see features on Venus that we do not see on other planets except Earth. Features that tell us that the surface is mobile. And in this example, we're looking at a sigmoidal graben features on the surface that tell us that this rift system is being sheared. It's what we call transtension, and a very common process on the Earth, because the Earth is made of rigid blocks or plates that not only move apart and converge, but actually rotate or shear past one another. And this is telling us the same sort of process is happening on Venus, albeit at a very different scale. And in the same way, this area with its sigmoidal folds or ridges is undergoing transpression. It's shearing as it's compressing. It's on a bend. Again, be careful of the foreshortening of the radar, giving you a false sense of vergence. So with all that in mind, we can start to map out structures and features with confidence, and we can then apply what's called kinematic models of formation. That's what this model here is. A shear in transtension will give opening features here, will give shear fractures here and here, and will give closing features perpendicular to it. And we can see a variety of those features in those orientations. We can see the opening graben, we can see the shearing surfaces. I'm not sure we can see any, well, maybe that's one of the compressional folds. But we can interpret those features as a transtensional structure. In fact, this whole area, I love this. George and I deliberately kind of underplayed what we were looking at because it was so radical to suggest there was this sort of big strike slip system. But the very next paper said, you've underestimated the size of it. It's actually 1,000, 1,200 kilometers across. And we said, yeah, we know it goes from there all the way up to there, if not a bit further. We only looked at this bit. And it's been debated ever since. Was it left? Was it right? What exactly is going on? In fact, almost certainly this is an area just like on Earth that has been sheared and resheared time and time again, because plate boundaries tend to persist over time. And this boundary between Thetis and Ovda, this is the edge of Ovda up here, Thetis is across this way, has probably existed for quite a while, with a lot of motion taking place. But that kind of detailed mapping helps us really understand what's going on. Another example here in Southeast Thetis, where we mapped out the individual thrust faults, and looked at their relationships, realized that they are abduction thrusts, not conventional subduction thrusts. So this planes unit here is riding up on top of this tessera area here, and you can see it sort of in the surface materials. We have to be a little bit careful about how we interpret these things, but we can see a variety of other processes as well. So in the highlands, we can see graben giving us extension and telling us that, that the high plateau, typical of a mountain belt, the high plateau, once it's fully compressed, then starts to extend in the more or less perpendicular direction. And so this is a classic orogenic belt, except that we have this plains abducting rather than subducting. And we see wind erosion and other features running through here. So this sort of blue area here is all wind-blown material that's sweeping around this high ground. There's a rift system up here, and there's other features to have a look at as well. And so we can start to make sense of the surface of Venus and its processes if we keep in mind the kinds of kinematic models that we use on the Earth, that we use to understand processes on the Earth. This doesn't mean ignore volcanism. That's equally important. And this example, going back to Scathach Fluctus here, illustrates exactly the kinds of things we need to do and the care we need to take with our mapping and to understand what's going on. There are very clear boundaries running through here, these lobes of the flows here, and we can see them actually because this surface has an unusual dielectric. It's a higher dielectric than most lava surfaces, probably because it's got a bit more titanium or iron in it than the typical lava surfaces on Venus. But the pyroclastic flow itself has a perfectly normal dielectric. And so on any other surface, it would look the same as that surface, but we can see it really clearly here. And we can then start to look at the flow in detail. We can see how it interacts with a small volcano here, how it interacts with each of these graben systems here, flows straight across them and terminates basically when it runs out of energy. It stops when it stops, if you like. It doesn't run out of material. It's flowing fast and comes to a stop. This is a technique using asperity where you can convert the image data into effectively roughness. It's actually much simpler just to use the image data, frankly, and to bear in mind that the transition in roughness is from about 4 to 8 centimeters roughness, and use the emissivity and other data. And I'll just leave you with this random image and thought, really, that I've been challenged in the past. Well, I challenge myself really to say, I think there is nowhere boring on Venus. You can look anywhere and find something interesting, find something you haven't seen before and others haven't seen before. And I picked this really boring area of Venus. It's just south of Ovda and Thetis, I think. And in there, in those dark, smooth, boring plains, with a bit of processing, with a bit of kind of open-mindedness, you can actually see a whole set of dune fields through here. And it turns out this is all ejected material from a big impact further to the southeast. And probably that's being reworked by surface winds on Venus, but you can see all these sort of ridges and patterns and so on are all dunes slowly migrating across the surface. Whether they're active now or not is a whole open question. But they were not recognized at all previously. In fact, only 2 dune fields had ever been recognized on Venus, so this is a third one. But it just goes to show you can sort of randomly go and look somewhere and find that there's something really interesting that you hadn't noticed before, and make new discoveries. So I think, Venus is actually probably the most exciting planet you can map even today, even with all the Mars data. if you're a geologist, if you're interested in volcanoes, if you're interested in structures and tectonics, Venus is the place to go.